I found a paper from some guys of his university in this application of wind farms, and then we started to talk about it, and this discussion at the end lead us to this workshop in the sense that he asked me to present something to the people of the university, and so this is the perfect match. And I hope you enjoy the presentation. I think it's very interesting. So Mario.
Thank you. So good afternoon, everyone. Before I start, I need to know the audience. So how many of you are engineers? Okay. How many of you? That's fine. That's fine. How many of you know what the Navier-Stokes equation is? Okay, good. How many of you know extreme seeking control? All right. So I think you have all the ingredients to follow my talk. I'm the director.
Otherwise, you would say, I'm not giving the talk.
No, otherwise I will say I will give you the ingredients.
Okay.
Just do a little preparation and come back. But other than that, it's fine. So I'm the director of a Center for Wind Energy at UT Dallas. For a number of years now, I have been working on applications of controlling wind in energy systems in general and wind energy in particular. And I find wind energy to be extremely interesting because it brings all the disciplines to solve a very basic problem. How do we produce energy without destroying the machines that produce energy? So that's the trade-off. Loads and life expectancy of the generator versus power production. And that's it. That's the problem that needs to be solved. So what I'm going to talk about is work that has been funded by industry on the application of controls to improve the production of wind energy in wind farms in a particular region of wind speeds. It's the region where the speed of the wind is not too low so that the machines can rotate. It's not too high so that we exceed the capacity of the generators, but it's in the middle, and that's called region 2. And that's the area where we want to maximize the power. Now, wind energy is about economy of scales. One turbine is not enough to connect to the grid and make money. Many turbines are, and that's why we have wind farms. So this is a problem. The basic problem I want to talk about, this picture is from an offshore wind farm off the coast of Denmark, and it was taken from a helicopter in a day where the atmospheric conditions were such that you could see the wakes produced by the upstream turbines, the one that see the wind first, on the downstream turbines, the one that are in the middle of the wind farm array. So this machine, for example, is being hit by wind, and then it's rotating and it produces this wake. And then you see in here and in here and in here there are other machines, but they are in the wake of the upstream machine. What that means is that they see lower velocity, mean velocity, which is what produces wind power, and they see also higher degrees of turbulence and fluctuations in the wind, which is what stresses them out. So this is not a good situation. So the point of the chart is basically the wakes reduce the production of energy throughout the year, and this is an actual measurement graph of power. One is the power produced by the first line, and then by the first row, and then as soon as you move to the second row, you lose almost 40% of the power because of the wakes. And then in a similar manner, the fatigue of the machines in the inner array also experience higher degrees of turbulence or fluctuations, and that fatigues them. Basically, they are rotating, but they are doing this. as well. So then the problem is, how can we control the different machines, the different rows, for example, so as to minimize the adverse effect of these wakes, which is aerodynamics interaction. We cannot get rid of the wakes, but we can mitigate their effect. So this is one solution. One solution is called wake steering. One thing I want to mention is, you may be thinking, why do you build a wind farm so that this happens? Why don't you spread the machines differently? Why is the layout the way it is? The point is that no matter what layout you choose, the wind direction changes with time, and there is always a wind direction where the machines are aligned. So this, you will never get rid of these, no matter how you optimize the layout. But one solution is to do wake steering by changing the rotor plane position. That's what we call yaw control. So if I am the rotor and my arms are the blades, and I would need a third one too, if I yaw, then I am deflecting the wake in the direction opposite to the way that I yaw. So this machine is deflecting the wake away from the ones downstream. And it may impinge on some of these, but their effect is not as significant. So basically, those bullets summarize what happens when you do wake steering. You can decrease the fatigue loads downstream, but you may increase fatigue loads upstream because now the first row is no longer facing the wind, but is in this position, and that means that the rotor, the blades are seeing a non-uniform wind as well. This concept is not new. This has several years now. But so far in the field, the majority of the tests have been done using open loop control. Just yawing the machines without any information about what they are doing to the power, what they are doing to the loads. It's just yawing the machines according to a prescribed schedule. And closed loop solutions are an active area of research. So our approach to this active area of research, first of all, the reason why I ask about Navier-Stokes is because trying to model the flow in a wind farm is an extremely difficult problem. You're talking about the interaction between structures and fluid mechanics at different length scales and time scales. You want to go from kilometers of the wind farm to the meters that are on a blade. These are very difficult things to model. So this has some of the ingredients that are for which extremum seeking is adequate. No need for a detailed model, particularly a flow model. In our approach, we need to know the layout, of course, because we use clusters. We don't control the yaw of every machine in the farm. We just try to identify which sectors of the farm are the one where the losses are the greatest, and then apply control there. And that means that we use cluster-based optimization in order to do that. And by clusters, I mean the interconnection of 3 to 5 turbines together. One thing that is an innovation, and we have a patent on that, is we don't maximize power. We maximize the logarithm of power. And I will show you why that is useful. And in particular, it's said in this bullet, once we calibrate all the parameters of the controller at one wind speed, it works at others' wind speed. And the wind speed changes a lot, from cut in to cut out, from cut in to rated wind speed. The other thing is that in this approach, using the logarithm reduces the sensitivity of the solution of the parameters that the extremum seeker needs to variations in wind conditions. This diagram shows how do we do this problem. So this is an image of our wind tunnel. You will see a lot of these images in the next slides with miniature wind turbines. In there, we measure their power. We decide how to form the clusters. That's done offline. Then we optimize with extremum seeking, and we close the loop to send the yaw commands to each of the machines. The clusters, we define them using that you can get very sophisticated and start looking at correlations of time series to decide which machine should be talking to which other machine. Or you can be very pragmatic and empirical and say, the ones that are close to me are the ones that matter the most. And that's what we do. We use nearest neighbor to decide how to form the clusters. And then we optimize the power of the cluster, for the power of each cluster. These papers that are in this presentation summarize the work. So now, why cluster-based LP? And then there are many versions of ESC that we have tried. And what I'm going to talk about today is something that Martin developed several years ago, which is PI-ESC. So to explain why the logo power, I'm going to focus on one machine only. Okay, so suppose this is my turbine. There are two inputs to my turbine. One is a control input. It doesn't matter what it is. The other one is the exogenous input, the wind. And then this machine produces power. We do some signal conditioning on the power. We extract the gradient. And the objective of the extremum seeker is to drive the gradient to zero because that's the necessary condition for optimality. That's why typically this is just an integrator. And if you want to be non-typical and accelerate the bandwidth of the closed loop system, you will start putting some lead compensation, like the proportional. And then you need to add a leader signal in order to have the persistence of excitation that is required to extract the gradient information. If you do the physics, the power produced by a turbine is proportional to the cube of the wind speed times the coefficient of power. And then you ask the question, what do we control here? Well, we don't control the wind. What we can control is the coefficient of power. It's like the efficiency of the machine. That equation is pretty much universally. Any generator has the multiplication of two things. The working fluid that is going to give you power times a controllable element that is its efficiency. In this case, efficiency is called coefficient of power. So why is this a problem? Well, the convergence rate of the loop that takes the gradient of power and therefore the gradient of the coefficient of power to zero is going to be proportional to V cubed. So you can be very slow at low wind speeds and very large and very fast, even unstable at higher wind speeds. So for a typical case that you go from 4 to 8, you can do the math, is 2 to the third, that's a factor of 8 as a change in the gains that are in the closed loop associated with extremum seeking. Or in a more modern world, the learning rate of the extremum seeker. That change could destabilize you, as I said, at high wind speeds and make you very sluggish at low wind speeds. So then one day I asked myself a question, without doing anything, is there a transformation I can do to my measurements in order to decouple the wind, which I cannot control, from the coefficient of power, which I can control? And if you think about this P wind is basically the V cube times some geometric parameters and air density. If you think about this equation, if you take the log, Now you have the logarithm of power is the log of the power in the wind plus the log of the coefficient of power. Now, any version of an optimizer that uses information from the measurements is mainly interested in the gradient. So if I differentiate this quantity relative to my control parameter, u, my control variable u, this thing goes away. So basically I'm going from multiplicative uncertainty to additive uncertainty, and when I differentiate, I get rid of the uncertainty. That's the theory, okay? So the log is very powerful. And if you have a background in communications or network theory or circuit systems from the 50s, that's when we started using decibels, maybe even before. And decibels are the log of power. So it has roots that go far beyond this interpretation. Now, if I apply the gradient method to the maximization of the coefficient of power, basically at steady state, this is what I need to reach, and this quantity is independent of the wind speed. And that was an interesting discovery. It led to a patent, and now we license that patent to a company that is trying to create a product with this concept. Why clusters? Well, if you touch all turbines in the farm, if you have 50 to 60 turbines, you're going to create a mess. So find where you're losing and fix that first. That's the idea of using these. And why PISC? Well, from everything we tried, it's the one that gave us the faster convergence to the optimal yaw set points. It has its issues, and I will come back to that at the end of the presentation. So everything I will show you are going to be experiments. There may be some equations hidden in one of the slides, but everything is our experiment. So we have a wind tunnel. It's a huge wind tunnel. It has a test section that is 30 meters long, and you see it here. And that allows us to build what is called the boundary layer, a scale atmospheric boundary layer that is representative of wind conditions in the real world. Then once we have that, these cubes that you see on the ground, they are roughness in order to promote the existence of turbulence and whatever you need to be more realistic. That's what my colleagues do. So in this case, this is a wind direction, and this is an array of 1, 2, 3 by 1, 2, 3, 4 wind turbines. And the wind turbines are in this picture. They have a rotor diameter of 0.2 meters, so they're small, very, very small. And we test them at properties of the flow that are consistent with what happens in the real world. When you scale down for an experiment in the wind tunnel, it's not just about making things smaller. It's not just about making your toy car. You need to scale down the aeroelastic properties, the aerodynamic properties of the blades, and so on. So these machines, the aerodynamics is close to what needs to be, but the aeroelasticity is not there. Aeroelasticity is the fluid structure interaction in order to understand vibrations. But I have another set of experiments that will solve that. So we've done so many experiments with these, and this is an aligned configuration. We also did configurations where we stagger them, and I may show you some of that. So how do we form the clusters? So in this case, we're going to put an extremum seeker in each of the turbines with a circle. And we are going to use the power of the squares to drive that extremum seeking. So for example, T1 is driven by the addition of the power of T1, T4, and T7. T4, extremum seeker, is driven by the power of T4, T7, and T10. We don't want to put too many. And the reason is time delay. It takes time for the flow to propagate from upstream to downstream. If we include too many downstream, we're going to have to wait quite a bit before we can update the controller or make the controller more complicated, but the delay cannot be ignored. So the objective is have a manageable delay and be able to increase power. So here is a case where we control row 1 and 2, and this is a case where we will control row 1 and 3. And for this case, we use a different set of clusters. We just use these two and these two 48, for example, these two 48, these two 42, and you can figure out the same concept for the other columns. The first thing we do is to try to understand where are the optimal set points for each case. And we do that open loop. So we start changing the yaw angle of the machines and measuring power to see where that is. And that's this plot. These are normalized wind power maps. So in this axis, there is the yaw angle of all the turbines in row 2. In this axis, the yaw angle of all the turbines in row 1. And in the graph, in the contour graph, what you see is the power when we move 5 degrees. I think we are stepping up 5 degrees apart for each yaw angle. And as you can see, when we don't yaw, we are at 0, 0, but the optimum is here. So we have to yaw row 2 minus 20 and row 1 minus 30. So this is typical. The first row is the one that yaw the most, the second one yaws a little less, and so on. The black circle is actually the optimum at this scale. The yellow star represents where the extremum seeking landed. So it found the optimum. And the power increase from no yaw in the machine, which is what is done in industry today, to doing this yaw is about 9%. So it's a good number. It's not a small number. Then this is the case where we do rows 1 and 3, and in here the increase is not symmetric, and there are some issues there with the rotation orientation of the turbines for that particular setup, and also the amount of power that we increase depends on the quadrant. So the actual optimum is that one, which is about 9%, but the extremum seeking converges to another optimum, another local optimum, which is about 7%. Feel free to stop me because these plots sometimes are difficult to digest or complex to digest, and if you want to ask me a question, that's okay.
If you want to ask you a question, back on the slide where you introduced the idea with power, I think it's a fantastic idea to clean up the Q. But ln of P in principle could be negative, the power somehow is. So you're using some kind of normalization of power to not get a negative number. Or maybe it doesn't.
No, it's never negative. When the power is negative, the machine is acting as a motor, so it's extracting energy to move the shaft.
So I meant the ln can be negative, but that actually doesn't.
Oh, that doesn't matter. That doesn't matter. We can shift it up and down. That doesn't matter. the main idea really is to take away the wind, but I like it even more because it makes multiplicative uncertainty additive uncertainty. That fact by itself has applications in other domains.
That's amazing. I've been trying to think of I think the trick is so awesome that one wants to find a whole catalog of other opportunities.
You know, when I don't want to brag too much, but when I presented this to someone, he said there is nothing more practical than a simple theory. And that was the case. So it's simple. But we introduce a nonlinearity. And it's a static nonlinearity that needs to be taken into consideration, the log. Okay, so here I'm going to show two things. On the left-hand side, I'm going to show yaw angles. On the right-hand side, I'm going to show the average of power calculated over central intervals that I will explain, and then the change in power relative to the baseline, which is no yaw at all, no yaw of the machines at all. So let's start with that. Well, let's look at this one. So what we do in the experiments is we run the experiments for 3 minutes in the wind tunnel without any control. And then at minute 3, approximately, we turn on the extremum seeking. Yeah, and that basically moves the yaw angle to the angles that you see here, -20 and -20 and -30, -20 and -30. We do 6 realizations of these with different initial seeds for the flow. And what I'm showing is with the arrows the increase in power for each of the realizations. Then we take the average power from 4 minutes to 7 and average over all realizations, average over that time interval, and create these plots. So here you see that the first row, the power goes down, and that's natural because the first row was seeing the wind like this, that gives it more power. You turn it, it's going to see less. So the first row goes down, the second row goes down. I'm sorry, this is the first row on the left, this is the first row on the center, this is the first row on the right. So these are all first row turbines, they all lose power. But then the turbines that are behind, they gain power. Okay? And those at this scale, they seem small, but they are not. And the same thing happens at the end. And here we show the average change in power between no control and full control. And this chart shows the percentage change in power for each of the turbines. So to make the point again, first row loses power, second row gains power, third row gains power, fourth row gains power, and the total farm power can go up to 9%. So just by forming these clusters, we already have these gains. You may want to see the time series that correspond to the, in the power signal, that corresponds to the yaw angles that you saw before. And these are the 6 realizations of the power signal. So what you can see is that at the beginning, when you turn it on, at this scale, the power comes down. And that makes sense, because if you're in the first row and you move, you're going to lose power right away. And then it comes back for the total power. So these are the 6 realizations that correspond to the experiment that I showed you before. So again, nothing surprising. Power goes up, and in the green area is where we do the averaging that show the charts that gave the numbers to the chart that I showed before, and in the pink area gives the no yaw control power. So this is the other case where we have only clusters that have rows 1 and 2 and rows 3 and 4. So now, if you just compare, the power increases are smaller than before, and that makes sense because of the way we are forming the clusters. And but again, if you look at row 1 loses power, row 2 gains power, row 3 gains a little bit, and row 4 gains a little more, and that gives the total power increase of 5.6. So one thing to be pointed out is that in the configuration where we alternate the rows that we yaw with yaw control, with the extremum seeking, the power increase is less, but the yaw misalignment is also less. And that's a good thing, because the less you are misaligned, the more uniform is going to be your mean wind speed over the rotor. Not the turbulence, but the mean wind speed. These are the convergence of yaw angles, and they are very fast. I mean, these are, of course, at the scale of the wind tunnel, we need to convert to the actual scale. Typically, that is done by doing a ratio of diameters. So these are 0.2 meters, and a 3 megawatt machine may have 120, 140 meters rotor diameter. So that ratio gives you how to scale the convergence time to the real time. So it's fast, and if we were to apply these, and it works, to a 15 megawatt machine, this IEA is a committee that creates reference turbines. It would converge in 12 minutes. Do we have a rigorous proof? No. There are no proofs here. The algorithm we used is this one. We take the power of each cluster, we average it over some window of time because the power signal is quite noisy, as you saw from the plots. Then we normalize the power before we apply the log. The argument of the log should be a non-dimensional quantity, and that's something that sometimes we don't teach in controls courses, the significance of normalizing everything before you do the controller, and then bringing those scale factors back into the controller. In this case, it's 1, so it means nothing, but it could be different. Then we apply the log, then we apply the PSC, and then we command the gamma. At a high level, this PI-ESC has two parts. One is the proportional and integral part, where this is the integral part of the controller, and this is the proportional part of the controller that creates the yaw command with the perturbation added to it. And the other one is the estimation of the parameter theta 1, which is related to the gradient. That estimation uses a model to predict the rate of change of the power, of the log of power, and then an update equation that is basically an equation from, I would say, system identification or adaptive control with a projection that is required to make these things work. The rest of the equation, this is a prediction error, this is a filter regressor, and this is the update of the inverse of the Hessian, if you would like. So that's what this algorithm is in a simplified form. There are many parameters that need to be selected, and there are even more parameters that are not shown here that are related to the set that is used for doing the projection. So in summary, for this part, what we have shown is evidence, and again, I use the word evidence because it's not a proof, but evidence that the cluster-based LPPISC can find optimal yaw angles without flow models. Power increases are quite good, and I don't think they are realizable in the field. In the field, we will see much less or less. And case 2 requires less yaw misalignment than case 1. So spreading, alternating rows may be more beneficial than trying to control consecutive rows, because you have some power gains without yawing the machines too much. Experiments are enough to do the calibration, but they are tedious. The students that did those went to the wind tunnel and spent quite a bit of time to get all the parameters right before we did the experiment. And I think that's an area of improvement for future versions of Extremum seeking. Convergence rates are very reasonable. The good thing of the log is you calibrate at one wind condition and it works at other wind conditions. But that's only true for the wind speed, not the wind direction. Because if you change wind direction, you may want to change what clusters you use, and you may want to adjust some of the parameters of the Extremum seeking controller. So what I was saying is that two of the parameters that are easy to tune, either frequency and amplitude, are basically determined from the dynamics of the turbine, from yaw to the rotor, speed or power. But the other parameters, the ones of the estimator, those were done by trial and error, and that took time. So there is a need for easier to tune low power Extremum seeking algorithms. And I'm not saying PI here anymore, because there are different classes of Extremum seekers, and finding the right one is what we need to do. And perhaps some of you are interested in helping us do that. So what I showed you are experiments on toy like turbines, these 0.2 diameter miniature turbines. Then we started conversations with people at Technical University of Munich who are experts in scaling down a machine so that you maintain the aerodynamic properties, the aeroelastic properties. Aeroelastic means how the blade deforms with the flow and how that influences the flow. It's a two-way street. And also the wake propagation. So they know how to do turbines that do that. And that's the G06. This machine has a rotor diameter of 0.6 meters. And in this paper is explained how it has been designed. The other good thing of that machine is that we are using an industrial controller for each turbine, and it's fully controlled in terms of controlling the pitch angle and controlling the RPM of the rotor. And has sensors everywhere, which means we can measure loads at the hub for the blades, for the shaft, and the base for the tower. So here we cannot put, because of the size of the tunnel is about 2.8, it's more than 2 meters wide and more than 2 meters tall, but we cannot put them side to side, because if we do that, then we end up with blockage effects due to the walls that are not real in a wind farm. But we can put them in line. So in this case, we use three configurations: the aligned configuration, where there is turbine 3, turbine 2, turbine 1. They are all on the same line. Then we move turbine 1 a quarter of a diameter to the left, and we move turbine 3 a quarter of a diameter to the right. That's the staggered left configuration because we are using turbine 1 as our reference for that change. And this is the staggered right, which is the opposite of that. And then we did the experiment again. So and here are the results for the 3 cases. We are controlling the first 2 turbines using the sum of power of all 3. So contour plots for power are shown here. This is gamma 1, this is gamma 2, these are degrees, units are in degrees, and the optimum is right there for the staggered left configuration. And as you can see, the dark circle is the one that we find open loop by sweeping over all possible angles, and the extremum seeker landed in there. And then the same thing happened in the stagger, but in the aligned case, that was not exactly the case. Now there is an artifact here, which is the resolution with which these contour plots were created. So we really cannot just say that this is a failure of extremum seeking. Then if we go through the experiment and look at power averages, if we owe for the staggered left configuration, the first one by 20 degrees, the second one by 10 degrees, we have a gain of 9.8% in power. In the aligned case, if we owe the first one by minus 20 and don't do anything to the second one, that's the 0 here, then and this is for the open loop map, then the gain is 1.5, but the gain with extremum seeking is higher. That's why it's in a darker spot than the black. We will see that in the next slide. And then when we go to the right configuration, same story as the left. You switch by 20, the first row, switch by 10, the second row, switch means change the yaw angle, and then you have a power increase of about 10%. So in this case, is the next one? Well, it's the one I have. So in this case, I'm showing you the staggered right, because the staggered right is the one that produced the most increase in power. So here are the time traces, time signals of the commanded yaw, and that sinusoid is the dither. We let the dither run all the time, but we can stop it once we know we have converged. So these are the yaw angles. This is the power signal, and this is a zoom in of this region, so that you can see again the convergence speed of the LPPISC. If we go in this diagram, I'm showing the configuration where, so this is the last turbine. The last turbine feeds in, gets added with the power of the with the power of the second one, and I'm sorry, gets added, goes in here, and that gives me the power. I'm explaining this incorrectly. So power comes from that side. So we take power, we do signal conditioning on the power for both T1, T2, and T3, and those signals are added to drive the LPPISC. The one for T1 is driven by all 3 turbines. The one for T2 is driven by 2 and 3 only. Forget T1. Delay compensation is required. In this case, the machines are bigger, and now there is some time delay as the wind propagates through the column of wind turbines. And that's included in the diagram. And then we put the LPPISC on T1 and LPPISC on T2 and do the experiment. So these are the summary of bar charts of power increases, and this is what I was saying before, that by changing the yaw angle of the second one, -5 degrees, we get a better result than the open loop map. But that's just an artifact of the discretization used to get the open loop map. Nothing different from before. Increases of 10% for the staggered configurations, and then a smaller increase for the aligned configuration. How much time do I have?
Hey, we're on time.
Okay, so this is the other thing that is important, loads. So what loads do we care about? We care about the machine doing this. It's called nodding or tilting. We care about the machine doing this. That's yawing. That's on the rotor. So nodding and yawing. On the tower, we care about the tower moving back and forth in front of the wind or side to side perpendicular to the wind. And the reason why there are double arrows everywhere is these are the directions of the vector, of the moment vector. Okay? With 3 different views, front view, side view, and top view. Those are the loads that we measure. And we go and look at the loads. And what we see is that for the fore aft, the tower moment decreases as you move along the column. Okay? And why is that? Because think about the first turbine. The first turbine was facing the wind. It's going to have the highest wind hitting me, so the fore aft motion is going to be more impacted. If I rotate a little bit, now I see a smaller wind magnitude, wind speed magnitude, and I'm going to move less on the tower. That's for T1. For T2, now we are providing more wind to T2. So if we are providing more wind to T2, the fore aft is going to increase. Then this is very logical. These two things are very logical, unexpected. And then the increases are shown here. This is the fore aft side for T1, T2 on the stagger left, and this is the fore aft side on T1, T2 for stagger right. And as you can see, decrease in the first turbine because I see less wind. In fact, what you see is V times the cosine of the yaw misalignment, all of that cube. That's what is pushing you. So it decreases there, but the second one sees more wind coming in, so they go up. The loads that I'm showing is called damage equivalent loads. That's a very technical concept that involves a lot of explanation, and I don't want to get into that for this audience, but just think about these as loads that reduce the lifetime of a turbine. And then for the hub, which is the nacelle, where the rotor is, there is some consistency in some cases, but in another cases is inconclusive. So in summary, by going to larger turbines, we continue to see evidence that this method works. And those are the first set of bullets. Again, we have to tune parameters, and the tuning can depend on wind direction. So this is critical for us. And right now, I'm looking for a postdoc in order to help me complete a project where we are going to do a field test on a real machine, on a real farm, in order to determine how well things can work. I think this is about loads. And again, what I'm saying here is that there is an increase in the fore-aft, that's in the direction of the wind, loads. These are damage equivalent loads. There is an increase as you move downstream, and that's expected. And the side-to-side moment decreases as we move downstream. So the machines that are further downstream do less of these. On the hub, we have consistency in one of the cases, and then we don't have a consistent trend for another of the moments. And I think this is related to the fact that now the turbines are larger, the orientation of the rotation matters to the loads, and the wall effects of the tunnel could play a role in that. And I believe this is the last one. So with that, I'll stop.
Thank you.